Good morning. My name is Kristen Tripp, and I am with the United States Department of Agriculture. I'm based in Corvallis, Oregon, and I'll just warn you ahead of time that it's 6 a.m. So if I'm a little slow on the draw, it's because it's 6 a.m. So today, I just really want to talk to you about this project that we're working on to expand a decision support tool so that it's useful for the entire United States. And that tool is called the Pacific Northwest Biochar Atlas. It's an online decision support tool suite that's available at pnwbiochar.org. And I do, before I start, just want to mention that a lot of this work was done by folks in my laboratory and by collaborators. In particular, Claire Phillips helped with this when she was a postdoc in my lab a number of years ago. So before I jump into the tool, I just want to tell you a little bit about myself to provide some context. In 2013, I was hired by the USDA as an applied microbiologist, and I was working in the lab trying to understand what sort of chemical signals bacteria and fungi put out into the soil to affect plant growth. And on that project, I worked with 5 other scientists: a pathologist, a physiologist, an agronomist, and a hydrologist. And within a year or so after starting on my work, everybody in my unit retired. I don't think it was about me, but I'm not super sure about that. Anyway, at the time, my research leader came to me and he said, Kristen, we have this extramural funding to look at the effects of biochar in a wheat system in Washington, which is north of where I am. And I'd really like you to take this on. And I said, yeah, you realize that I have no field experience. I've never done an agronomy experiment. I've never grown anything outside of my home. And he just kind of gave me this look of sympathy and was like, you got this. And I said, okay. So we went up to this farm in eastern Washington, where they usually try to grow wheat on soils that are about a pH of 4.5. These are soils that are historically forested, and due to many decades of mineral fertilization, the pH of those soils have dropped significantly. And it's really hard to grow wheat on pH 4 soils simply because of aluminum toxicity. So we decided to add 8 tons an acre of biochar to bring up the pH. And we were able, after a year, saw that yield increased by 278%. So in that experiment, we added had plots that didn't have anything added to them. We had plots that had lime added, and then we had plots that had 8 tons or 16 tons per hectare, 16 tons per hectare of biochar added. And you can see that we significantly increased yield. We're really excited about these results, and you can see what those look like here, where we've got biochar that was added to the soil versus the control plots where you can see the wheat is growing really poorly. And these photos were taken at the same time. So this was in April of that year. And you can just see how dramatic of an increase we had. I was really happy with these results. And I went back to my research leader and I was like, hey, Gary, look at these results. They're pretty impressive. And he's like, well, why don't you try in a different cropping system? And so I worked with a collaborator across the street looking at blueberries. And in here, we added blueberries to these pots at 20% of the volume of the pot. And you can see that, here's 10%, here's 20%, and then we did a bokashi biochar mixture. And you can see that we significantly increased over the control in both the shoots and the roots of the system. So we did another experiment to just confirm this, and we saw similar results. So we were really happy with this, and I went back to my research leader, and I was like, Gary, doing a good job on this, pretty excited. So we tried it in the field. And so in the field, we saw similar results where we had a whole bunch of different amendments that we added. But if you just look at biochar in the planting hole at 10% versus the control, which is either sawdust or soil alone, you can see that we had a significant increase. So again, I was really excited about this. And so we tried it in grapes. And in grapes, we added 8 to 16 tons an acre to these fields. We had a no-till control, ones with biochar that was not added, biochar that was added at 8 tons an acre, and biochar, or 8 tons per hectare, biochar that was added at 16 tons per hectare. Oh, hang on. And you can see that we had no change in yield. And we were pretty disappointed by these results, but we thought, oh, this is just a one-off. Let's go ahead and do another weed experiment since we had such great results, and we'll put them at 6 sites across Oregon. So here we've got 2 kinds of biochar. We've got a wheat straw and another sort of conifer wood biochar. And you can see at these 6 sites, as we increase the biochar amendment rate per mass, we had no increase in yield. And so that was fairly disappointing. And we were really wondering why we had such great results in Washington, but such poor results in Oregon. And so just to recap sort of my experience over my first few years, wheat and blueberries, we had a great result. And then in grapes and wheat in Oregon, we had very little increase in yield, if any. And we also saw, negative results when we put biochar in the rangeland and biochar in hops, and biochar in row crops and biochar in grass seed. And while this was disappointing, especially since I had been going back to my research leader and telling him how awesome of an agronomist I was, it made sense. And if you go back to the literature and you look at meta-analyses, this is one from 2017. Certainly there's meta-analyses that are more recent than this, but you can see that we expect these results, that adding biochar to soils is difficult to predict the response. So we just look at the grand mean, you can expect maybe a 10% increase in yield, but that really depends on your soil pH, on your latitude, and the feedstock type in both the tropics and in temperate environments. And so what this got me thinking about, especially in conversations with my colleagues, is that biochars are not all created equal. So again, if we just sort of, look at this little diagram I made from biochars we have in the lab, if we compare biochars by particle size, you can see that they increase as depending on how the feedstock is processed, but depending on the temperature in the seed waste biochar, as you increase the temperature, you have more ash. And so, of course, we all know this about biochars, that the feedstock and production conditions impact physiochemical properties. So if we just take 2 of those biochars and we look at the proximate analysis, the poultry litter biochar has more ash in it than a hazelnut biochar, which has more stable carbon. But as you increase the production temperature, this also changes. So this volatile section in the hazelnut, this volatile fraction goes to a stable carbon, whereas in the poultry litter, the volatile carbon turns to ash. And so this has really dramatic consequences for crop response, right? If we have that big ash fraction in poultry litter, we're going to have more of a fertilizer value, which is shown in this graph here with P and K, and then more of a liming value as well. So understanding how biochar can react is really in soils is really an important thing. And this doesn't just pertain to approximate analysis. Of course, as a whole host of properties, including hydrophobicity, water holding capacity, liming values. So in order, the lesson that we learned from this is that in order to use biochar effectively requires identifying management goals, identifying a biochar that can meet those management goals and find a rate that meets that need. And so when a grower calls me and says, I'm really interested in implementing biochar practices, I don't have a right answer to give them because, of course, biochar is not a one-size-fits-all solution. Biochars vary in their physical chemical properties and the types of benefits they can offer, and soils and crops vary in their deficiencies. And so the answer to this fundamental question of what kind of biochar to use and how much to use is consistently, well, what are you trying to accomplish in your agronomic system? What's the limiting factor that you hope to ameliorate with biochar, and how much biochar do you need to accomplish that? And to sort of skip to the punchline is that in order to get the most benefit from biochar or any soil amendment, you have to identify cropping goals, identify product that can meet those goals, and use those products at a rate that makes sense. And if you're familiar with the principles of nutrient management, this sounds a lot like the 4 R's, right? The right rate, the right place, the right source, and the right time that are important for correctly utilizing fertilizer. So using biochar to improve crop health or soil health for that matter requires similar thought. So in order for farmers to help make this decision, we developed the Pacific Northwest Biochar Atlas. The tool is available at this website here. And when you go to that website, you've got a lot of cute little flip boxes where you can learn about biochar. You can find a biochar that meets your needs. You can read case studies, find producers, and you can compare biochars. But what and this tool was originally made for the Pacific Northwest of the United States. That includes Washington, Oregon, and Idaho. So it is very limited in scope. But let me tell you about it, and then I'm going to talk about how we're going to expand this to the entire United States. So again, this is kind of the algorithm behind it, and the thought is to again use these sort of nutrient management tools to apply them to biochar. So this tool allows you to make biochar decisions in 3 steps. The first step is gathering information, entering that information into a tool that'll help you identify goals for your soil, your crop, and identify a biochar. And then the third step is estimating benefits using just sort of a calculator-based algorithm. So this first step is gathering information. So you're going to require a soil health analysis and a crop that you're growing. You can either get this information from a soil test, or if you're in the Pacific Northwest, you can pull up inherent soil data using this mapping interface. These are NRCS data that are publicly available. And these tools will tell you about your soil series, physical properties, moisture properties, and chemical properties of your soil. So after you type in the information, you put in information about carbon, soil fertility, acidity and buffering, and texture. Again, these are all usually on a soil test report, or you can pull them up from our online tool. And then what it'll do is it'll tell you about your soil carbon. Is it low? Is it medium? Is it very high if you're in an organic soil? It will also tell you about the fertility of your system. Of course, this depends on which crop you're in. And so we have the back end of the tool has about 40 crops populated in it, and it'll tell you whether or not your phosphorus, your potassium, and other nutrients are what range they're in. It'll also tell you about soil acidity and soil moisture. Now, from that, you can start to think about, what sort of deficiencies do I have in my soil, depending on my crop, and you can choose 3 goals. Now, the first goal that I'm going to choose for these soils are sequester carbon. The soils that we were in Eastern Washington were very low in organic carbon. We want to increase the soil pH, and we want to increase water retention. I will say that there are a lot of other goals here that are available for selection. Now, based on which properties I select, the biochar tool will take me through a selection process. It'll tell me which biochars meet my first priority, which was sequestering carbon. It's going to choose sort of these high carbon, high temperature wood biochars. Priority 2 was increasing pH, so it's going to grab these more ashy biochars like poultry litter pellets. And then priority 3 was increasing water holding capacity. So it's going to ask me, or it's going to query biochars that have a small particle size. And then it will also tell me that this Oregon white oak biochar is my first choice because it meets all 3 of my goals, whereas this Douglas fir biochar only meets 1 of them. And so from this information, I can choose Oregon white oak. I can choose which which units I want to use, whether imperial or metric. And then it'll tell me how much benefit I'm expected to get from those biochars based on an application rate. It'll tell me how much stable carbon I'm adding, phosphorus, potassium, sulfur, and magnesium. And so this will allow me to decide how much of a nutrient requirement, or allow me to know how much of a nutrient requirement, how much liming requirement, how much stable carbon I'm adding to my soils. We also have a cost benefit analysis tool on the website. So what you can do is you can add in your biochar costs, what the crop value changes you're expecting, whether it's a positive, negative, or neutral value. You can reduce or increase crop inputs, and that'll give you a total result. So for example, in this situation where we added 1 ton of biochar, we decided that biochar was going to cost $500. We expected a small increase of in profits, and then it'll calculate a net benefit over 5 years. I can discount this benefit in the tool, and in this case, it'll show that the farmer is having an increase over 5 years of $1,000. So this is the tool, but it is really limited in the moment. The map function is limited to the Pacific Northwest. The crops are limited to crops that are grown in the Pacific Northwest. The biochar database that we have are particularly lab-grown biochars. And what I mean by that are biochars that we've produced and characterized in the lab. Our biochar directory of producers is outdated. There's no greenhouse gas model or carbon sequestration model in the biochar atlas. And the problem with the economic analysis is that it really is based off of yield. So if you don't have a yield increase, you're never going to show success in your economic model. So if we go back to the story I told you about in Eastern Washington, where we had this 280% increase in yield, in that case, let's just walk through the economics real quick. So in that case, we applied 8 tons an acre. So let's say that's $500 a ton for biochar. We increased the crop yield by 280%. And in wheat, that would mean a change in crop margin of $763, given the current prices of wheat. And you can see that even over 5 years, with these dramatic increases, we still have a negative net loss in our crop margin, just because the cost of the biochar was so high and the cost of the commodity was so low. But what happens if the price of the biochar is zero? I know that sounds a little bit fantastical, but in the United States, the Natural Resource Conservation Service just adopted Conservation Practice Standard 336, which provides technical and financial assistance for biochar application. In the United States, this means that the government will offset the cost of biochar compost or biochar compost mixtures. The payment rates are based off of application rates of 4 cubic yards per acre of biochar, and you can apply that over 3 years for a total of 12 cubic yards per acre, and then various compost and biochar mixtures on 20% increments. So 80% biochar, 20% compost, all the way up to 80% compost, 20% biochar. This can be obtained by going to your local NRCS agent and putting in an application for CPS 336. So the reason this is so cool is because it changes the value proposition of biochar from a yield proposition to a conservation proposition. So instead of relying on yield to offset, we're really relying on these conservation benefits, much like no-till or cover cropping is applied in the United States. And so again, let's go back to this story in Washington and see what would happen if the cost of the biochar was zero. Again, we'd have a zero cost for biochar. The change in crop margin would remain the same. And instead of having a net negative change in crop margin, we would have an increase of $3,815 per acre. So what I like about this so much is that it changes that proposition value from crop yield to carbon sequestration. And in the United States, that's just really a game changer. So as I said, we're expanding this tool to the entire United States, in particular to support implementation of Conservation Practice Standard 336. To do that, we're developing a biochar database. I'm doing this with many of my colleagues at USDA ARS. I think some of them are on the call, including Kurt, Isabel, and Steve. So we're distributing biochars from actual producers to over 10 USDA laboratories. We're conducting tests to measure IBI standards, and publishing those results on our website, and then using them to populate this database that we'll have, hopefully of hundreds of biochars. And here's where all of my collaborators are located. We're developing a greenhouse gas and carbon model so that we can put this into crop decision support models like Carpe or Comet Farm. This is being done by Washington State University and Jim Amonette. We're increasing the map function and the crop function of the database in collaboration with Oregon State University. And then we're working with American Farmland Trust and USBI to do farmer and conservation planner outreach on the tool. We're hoping this tool will be developed over the next couple of years and will be available for public use. However, I encourage you to go to the website now to give us any kind of feedback about how to improve it. We're also in talks with IBI to see if we can find funding to create a global model that does similar calculations. I just want to point out that we've also done a lot of other sorts of development of tools, including fact sheets. These are about agricultural application. We've also done some on manure management, stormwater management, carbon markets, and lab analysis and interpretation. These are available at the USBI website. We have an FAQ and an Excel spreadsheet that'll help you work through some simple calculations about biochar. And other tools that are available on this web address. And with that, I just want to put up my email address. In case you guys have questions and we don't have time in the chat, feel free to reach out to me. And again, thank you for your attention. I appreciate it and would welcome any feedback. Thanks so much.
Thank you very much, Christine. That was very interesting and also very helpful, unfortunately, in the US. So I would really like to see that in Europe as well. And my first question would be, how difficult do you see it to increase the geographic range for this? Is the range thing, is it a more simple way of increasing the model?
So right now the tool, let me escape out of here so I can see all your beautiful faces. I think right now the tool is really simplistic, and that's, I think, why it's so elegant. And the back end of the tool that sort of queries all of these biochars and queries all of these soils is really what makes it the geographical limitations, the geography of the tool so limited. But these are pretty simplistic calculations. So I think that we can, if we're going to expand it globally, I don't think that we need this fancy back end. Instead, what we need to do is just develop input so people can either put in information that they have from a soil test to sort of prompt the decision support part of it. They can also put in, properties of the biochar that they're interested in. To see if they can find one that, or they can use the tool to find something that matches. So I do think that we can expand this globally by making it more of a user-driven field than relying on the back ends. We're working to build a collaboration with others in Europe to build that back end of the database. I will say that I think the other thing is that, getting a soil test is a pretty developed country thing, right? It's hard for somebody in sub-Saharan Africa or in Asia to go out and get a soil test. And so we're looking at ways that we can qualitatively assess soil health in the field to apply these same principles.
Okay, yeah, I guess that's one of the limitations if you're in certain parts of the world. But it's good to hear that you're already working on the European side at least. And I'm sure there is a lot of interest from the EBI and so on. So John Hoffmeyer was asking this question going into a similar direction. Is there a way to use your database in reverse? I'm thinking of establishing the characteristics of a soil in South Africa and then finding a similar soil in the PNW in order to use the tool as a rough guide.
I think so. So one of the things that we did was we also built an Excel-based spreadsheet that again is really simplistic, where you can put in your characteristics of your biochar and then figure out things like how much P and K it's going to provide for soils, how much carbon it's going to apply for soils. What that spreadsheet doesn't do is what you just asked, is looking at different soils. Could you use it in the reverse fashion to find a similar soil? It doesn't have that functionality now, but I think that's a really great idea.
Okay, so there's a new outreach going on then. Nabila Salsabila from Indonesia was asking, Did you also give the recommendation on how to charge the biochar? So basically, if you apply it with a fertilizer on top of it.
Yeah, so no, all the biochars in the database right now are raw biochars. I think that when the tool comes out, we'll have the opportunity to add in characteristics for what a biochar looks like prior to addition. So if it's a biochar compost mixture, that should be analyzed beforehand, and is required to be analyzed beforehand by the NRCS. So, so you can add in those properties of what the charging looks like. And the reason that we don't do that is because it's very difficult to predict how charging changes the biochar. But if we ever develop that theoretical framework, I would love to add that into the system.
And the follow-up question from her was, have you ever conducted research using the recommendation from the calculator and checked the yield improvement?
Yeah, we did. And so, hang on, let me share my screen again really quickly, and I'll go back to these results. Let's go back here. Oh, here we go. Sorry. So here we go. So this is actually what these data were taken from in a paper where we tried to validate the tool. So the tool does not predict crop yield, right? So one would have to predict crop yield for the economic analysis. And that's just because crop yield is just really difficult to predict. But here, what we did predict from the tool that I'm not showing is pH increase. So one of the reasons that we didn't see yield improvement is because the pH of all of these soils was already optimal for wheat. So it was at about a pH 5.5. The only one where we increased pH above the recommend or to the recommended value were in these soils here. And you can see that with some of the biochars, we actually did have an increase in yield that was, predictable with that pH response. And so the tool does do a good job of predicting what the changes to the soil will be. It's really up to the farmer to kind of predict how those changes are going to manifest in a yield increase.
And maybe one last question for myself is, so what kind of characteristics are you checking when you check a biochar? Because I assume you cannot check all of them. The pH will be important, the nutrient value, but is there anything other that jumps out?
So we're actually going beyond the IBI standard. So we're doing everything that's recommended in the IBI standard. And then depending on which capabilities these laboratories have, almost everybody has sort of their favorite analysis that they're doing. So for example, I think that Kurt's doing X-ray diffraction. I can't remember that off the top of my head, but everybody's got their own little tools that they're interested in. And so we are doing IR spectra and other analyses that are beyond the IBI in hopes that these data will also be useful to researchers who are interested in either obtaining the biochars or using the data to understand how production and feedstock influences other characteristics that are not listed in IBI. So we're doing more than is required.
Okay, that also answers the last question. Is there biochar properties versus performance relationship generic guideline? And I guess not yet.
Yes, that's right.